Hello everyone, welcome to our first episode of Solving NCPHO problems. Today, we'll be solving problem 25, Cherenkov radiation in water, from our recent January competition. So you may be wondering, what is Cherenkov radiation? This is this type of radiation that occurs when a particle moves faster than the local speed of light. You might be wondering, how can this be? Didn't Einstein say that nothing can move faster than light in general relativity? That is true, but only in a vacuum. In denser mediums, light slows down and it becomes possible for very energetic particles to move faster than the local speed of light. This is what causes the blue radiation that you see in the water of nuclear reacting plants. Anyways, let's get started. So we got a photon, class of the free electron, mass 31 times 10 to the negative 31 kilograms. All energy is transferred as kinetic energy. And we have an index of refraction of the water as 1.33. So we're going to ignore every energy loss and we're going to use significant figures. We need to find the minimum initial frequency of the photon so that Cherenkov radiation will be generated. So firstly, in case you didn't know, our index of refraction n is given by c over c naught. C is the actual speed of light and c naught is our local speed of light. We want to solve for c naught. This is simply c over n. We can plug everything in. The speed of light is 3 times 10 to the 8 meters per second over 1.333, and this gives us a very nice 2.25 times 10 to the 8 meters per second. So this is our local speed of light. So the speed of our electron has to be more than that for Cherenkov radiation to form. So knowing that, we can look at our kinetic energy. This is, as you know, 1/2 mv squared. We know the mass as 9.1 times 10 to the negative 1 kilograms. We know our velocity as this. So we can just plug everything in. 10 to the negative 31 kg, 2.25 times 10 to the 8 meters per second squared. And this will give us a very nice 2.3 times 10 to the negative 14 joules. So this is the energy that our electron has. So next, we need to figure out the energy of a photon. So in case you didn't know, E photon is equal to Planck's constant, or H, times F. H is equal to 6.626, or 6.626, times 10 to the negative 34 joule seconds. Plugging this in, if you want to find our frequency will be simply given by energy over Planck's constant. We already know our energy, 2.3 times 10 to the negative 19 joules, and we know Planck's constant, 6.66 times 10 to the negative 10 to the negative 34 joule seconds. Over 6.626, 10 minus 34 joule seconds. And when we do that, we're going to get a frequency of 3.5, of roughly 3.5, times 10 to the 19 hertz, meaning our answer is C. Thank you all for learning with us. Stay tuned, watch more videos, learn more physics, join NCPHO. Thank you.